Good afternoon, everybody in Taiwan, and good morning in Europe, and whatever time in United States, if somebody listening to this program from America. So very, very happy today to have been able to invite Professor. Now he calls himself doctor because he's now working at the laboratory. Dr. Luc Bergé. He is the laboratory head at the I would say that Commission, right? Commission of Atomic Energy, French Atomic Energy.
Yes.
Yeah. And he is an expert. He's a theoretician and he's expert in when you call it nonlinear optics and in plasma physics. And I read it from the I think I read this announcement 5 years ago when he won the prestigious Gettner Kessler Prize, awarded by both the German and French physical societies. I think that he worked a lot. For one thing, he worked a lot for the cooperation between France and Germany in physics. Hope that in future we will be able to also to work together between Taiwan and France. I mean, I would say in Europe because he is now the president of European Physical Society.
Yes.
And his specialty is in modeling of nonlinear wave propagation, especially in the femtosecond laser filamentation, the terahertz pulse generation. And I think he will say a few words about the wide application of this new technology to the ranging from fusion physics to even to I think to atmospheric physics. Okay, I would not say too much about Dr. Luc Bergé now because he's going to explain more about him and also talk about the EPS, the European Physical Society, is doing, and also about the great challenges that the EPS is posed, to as a guideline for development in physics. Yes, Luc, please.
Thank you very much for the nice introduction, Wing. I do appreciate that. I will just correct one point. I'm no longer head of a laboratory at the CEA since I've not been since a few months now because I moved to Bordeaux University quite recently. But apart from this point, I mean, everything is completely correct. I'm going to share my slide. Would you like? Yes? Chuck?
Yes, please do. Great. And can you make it full screen? Yes, now it's not full screen. Yes, please.
It is full screen, no?
Yeah, it is. It is. Yeah.
So everything is fine.
Yeah.
Can I go? Yes. Okay. Okay. Yeah. Yes. I mean, you see. So I work administratively at the Commission for Atomic Energy, and since a few months now, I have moved at Bordeaux University at CEGA Laboratory, which means Center for Intense Lasers and Applications, where I work by forming and training PhD students and looking after activities linked to laser-matter interactions. So first, I would like to thank very much Wing and Luc-Huen, I mean, for the kind invitation to give this talk. You see the title is not so common, intense terahertz fields. So this will refer to the science I'm working now and new perspectives on the European Physical Society. As Wing said, I mean, I'm the current president of the European Physical Society, and I would like to share with you some knowledge about how the EPS works and what are also the challenges we are facing, not only in science, but also from a more societal point of view linked to the physics, of course. Okay, a few words about the place I've been working, and I'm still attached to it, at CEA. We are more interested in my branch to the fusion, the thermonuclear fusion resulting from the action of very powerful laser beams interacting with a cryogenic target, which is here. I don't know, do you see the arrow when I do that?
Yes, yeah, we saw your cursor, yeah.
Super, thank you very much. As probably many of you have heard of, last year in December, there was a real breakthrough achieved by the Lawrence Livermore National Laboratory that hosts what we call the National Ignition Facility in the US. That consisted in achieving and realizing, the break-even. The break-even is when you make an active fusion gain. That means that when you put, for instance, a target, which is this ball here, filled in with some deuterium and tritium, you can realize the fusion process, transforming these two elements into alpha particle or helium isotopes plus neutron. And when you exceed a certain yield of neutron, then you are sure that you have realized the fusion, but the point was to get more energy than the energy delivered by the laser beams. Typically, this was this feature that was achieved 1 year ago, and it was repeated last August, and even repeated 1 month ago at the NIF at Lawrence Livermore National Laboratory. So this is a way for producing energy, and the principle is to make powerful or energetic, I would say, laser beams interact with a capsule filled with or covered with some gold, and that contain this target containing the fuel, deuterium plus tritium. The philosophy is to make what we call an indirect drive illumination of this target. That means that the laser beams are not going to impact directly the target, but they will impact the walls of the whole home. So this capsule creates some X radiation, and the X radiation are going to is going to compress the target isotropically. And you can see this measures what, a few centimeters. It is located at the very center of the experiment chamber here. And here you have the size of the experiment chamber covered by some, here, this metal, but these are glass windows that let the laser beam come into the experiment chamber and be focused at the very center of this chamber. You have here the same experimental chamber, but at NIF, and this is the one we have in France at the Megajoule Laser Facility. And this facility is linked to some of my activities at CA. So you can imagine that a very large facility offering many laser beam lines. Typically, we have 22 lines composed of 2 quads, composed each of 4 laser beams. So this means 176 laser beams. You have to imagine that they make 40 centimeters per 40 centimeters. These are square beams that are focused over a few nanoseconds to the chamber, to the center of the chamber here. And the duration of these beams are nanosecond. We use a relatively moderate intensity, 10 to the 15, and you have many problems attached to the physics of the plasma that you create, because first, you ionize your target and you create a plasma, among which you develop some instabilities, hydrodynamic instabilities, but also laser plasma instabilities, which are difficult to control. But anyway, this breakthrough was achieved, and we are trying in Europe, in particular at the Megajoule Laser Facility near Bordeaux, to repeat this breakthrough by using, these performances from the laser point of view. And you see here, I put petal, that's one line, one beam line, which is a petawatt laser, excuse me, delivering less energy. I'm talking about 10 kilojoule laser energy for the main driver. But for these pulse, this an ultra short pulse or femtosecond pulse, 500 femtosecond duration, and the beam deliver 3,500 joule within 500 femtoseconds. So the peak power nowadays is above 1.2 petawatt, and you can achieve on target some very high intensities above 10 to the 20 watt per square centimeter. And this beamline is used to produce some particles, to accelerate charged particles, electrons, ions from a conversion target, for instance, and to probe with the beams which are created from this conversion target, to probe the plasma which is formed here and have some information about the electromagnetic field, about the temperature, about the plasma density, and so on. So this is the main activity of the place where I come from, basically. It happens that, as Wing rightly recalled, I worked on several topics, starting from applied mathematics, describing the self-focusing of optical waves in nonlinear materials, in gases or in solids. And then I work more on laser filamentation. That means the balance you realize between the optical self-focusing and the creation of plasma that allows some femtosecond light beams to be guided over very long distances. And more recently, I've been working, because I'm still continuing to work on that, on the generation of terahertz waves. Terahertz waves are some electromagnetic waves, entities that are comprised in the electromagnetic spectrum between the optical wavelengths you have here and what we call the electronic domain, so microwaves, radio waves, and so on. So, I mean, they are in between, extending between some hundreds of gigahertz and, let's say, 100 terahertz, and they escape to the main means to produce them. So they are relatively difficult to produce. So nowadays we know how to produce them using long antennas or photoconductive switches or quantum cascade lasers or even optical rectification from crystals. But from my point of view, or in my activity, we have been busy in producing them and using them, starting from gas plasmas. Typically, these waves are characterized by wavelengths, which is rather long compared with the optical light. Typically, I mean, the wavelengths extend from 10 micrometer to 1 millimeter. And they have some very nice properties, like propagating over a few millimeters of light materials or tissues like skin, fabric, plastic. Typically, they can be used to diagnose some skin cancers. So they propagate a few millimeters across the skin. They are rapidly absorbed by water, but I mean, this property allows the researchers to identify, for instance, here the cancer cells, the cells of a tumor, which you cannot do by using visible image, for instance. You cannot use this property of penetrating layer by layer of the terahertz waves to use them for the cultural heritage. Typically, I mean, you scan layer by layer a painting here when you don't know the author, and this is a nice example. And by doing this, when people working for museums, they arrive to identify the signature of Goya. And they were quite happy this day to make such a discovery. But usually, for these applications, terahertz fields are employed at relatively moderate level of field strength or of amplitude. Typically, I mean, you do not exceed some kilovolt per centimeter. You can use terahertz fields for doing other activities, making ultra broadband spectroscopy, for instance, or making active manipulation of matters. If you succeed in reaching some field strengths being above 0.1 gigavolt per meter, typically. And this is by doing such very strong terahertz fields that the team led by Kate Nelson at the MIT in the US succeeded in changing the properties of some atom arrangements. You see here a crystal formed by different atoms of a crystal, and they have some properties like being paraelectric materials, and they succeed in inducing a magnetic momentum by making a terahertz pulse moving a little bit far apart one of the atoms in order to change the property of this material and make it being more ferroelectric. This is an example. Another example in France at the University of Rouen, a recent one, was to use an intense terahertz pulse interact with the very extremity of a metallic nanotip in such a way that locally the electric field of the terahertz waves can be hugely amplified, and even being the possibility of extracting the constituents of this metallic sample. And by doing this, the terahertz waves, which is a long wavelength object, was able to accelerate the different particles, so the ions, the electrons, and by making some measurements of the time of flight of these particles, the authors could be able to identify the structure of this metallic nanotip. So this is called atom tomography. I mean, you can find in this review paper, which is a very nice review paper, many other applications requiring ultra strong or strong terahertz fields. What I worked on more particularly was an emitter of terahertz waves composed simply by a plasma of gas, and even more naturally, a plasma of air. Typically, the process is the following. You take an ultra-fast laser source, a Titan sapphire laser source, operating at 800 nanometer, for instance. You take the fundamental pulse, and you make it pass through a doubling crystal, a baroborate oxide here, that produce a fraction of second harmonic. So you have a wave beating at omega 0, and you create 10%, let's say, of another wave beating at 2 omega 0. And you focus both these components at, let's say, 20, 30 centimeters from the length into the gas, into air, and you form a plasma. And the plasma is a nonlinear medium that will mix up these two frequencies. Typically, by mixing them, you will create some higher order harmonics, 3 omega 0, 4 omega 0, 5 omega 0, but by doing what we call down conversion, you will be able to subtract one photon beating at 2 omega 0 with 2 photons beating at 1 omega 0. So of course, when you make such kind of subtraction, I mean, you have not zero frequency because zero frequency is not physical, but because you make this conversion starting from ultra short laser pulse, having a broad bandwidth initially, you subtract some large bandwidth, and by this down conversion process, you are able to reach a domain in frequency which belongs to the terahertz domain, and which is quite low compared to the wavelength range of the optical components. And the ultimate process for generating the terahertz waves is the ionization process. You need to work with some intensity being around 10 to the 13, 10 to the 14 watt per square centimeter. That means that you are going to extract the electrons from the molecular constituents of the air, from the atoms, and at each extremum of the laser pulse, you will extract a certain population of free electrons that will be further accelerated by the laser beam. And this is this further acceleration that creates a burst of electromagnetic wave. And if you want to have a low frequency burst, then you need to break the symmetry of your laser pulse. And this is done by the addition of the second color. And you can monitor the asymmetry of this pulse, of this distorted pulse, by the relative phase between the fundamental pulse and the second harmonic. And by doing so, you see the green curve here, that's the electronic current. The electronic current, that's basically the product between the elementary charge, the electron density that is growing fastly inside the pulse here, that's the red curve, and of the laser field, this black curve. And when this black curve is distorted, you can make the calculation and show that the current density after the laser pulse history develops a quasi-DC component, so a low frequency component that corresponds to the emission of terahertz waves. And by this, I mean, we can achieve quite interesting field strength and quite interesting frequency range. We used these waves produced by what we call a two-color plasma, or plasma created by a laser having two harmonics, by using this kind of setup. Typically, you take a laser, a titan sapphire laser, delivering a 30 femtosecond laser pulse, 1 kilohertz repetition rate, arranged in a pump probe setup. The pump part is used to be focused, pass through the BBO, and create a two-color plasma. So you create a second harmonic, and the plasma radiate many frequencies, and you guide these frequencies through a setup of 4 parabolic mirrors, in which, I mean, you put a silicon wafer here in order to filter out the optical component. So you are only left with the low frequency component of the radiated field. And this radiated field, I mean, can impact either a hole for getting a reference terahertz field or a sample which contains the molecule you want to analyze. And you guide the transmitted signal to the detection zone. And this detection zone hosts a high voltage module that delivers an electric field, what we call a bias field, that will couple with the transmitted terahertz field. And you see here, the probe part is arranged as a delay stage in order to have a control of the time increment, femtosecond per femtosecond. And this optical beam is used to switch on the optical nonlinearities of air. So you couple basically 3 electric fields: the optical electric field, the terahertz electric field, and the bias field, which you control, that is delivered by this high voltage module. And you measure the second harmonic of the overall intensity. And you, by making simply the calculation here, I mean, you can demonstrate that you have a signal that is typically dependent on the bias field, which you control in amplitude and in phase. And you have also the terahertz pulse, which has been transmitted, that evolves with the time increment you can control through this delay line. So this is a very nice setup named air biased because you use an electric bias field. Coherent detection, coherent because you have the information of your terahertz field in amplitude and in phase. And this is typically the signal you get. The black curve, that's the terahertz field, which is a single cycle terahertz field. When you have collected, when you have no sample, and the red curve is a terahertz signal, which you can measure for a sample of, in that case, it was a thymine. So we put some thymine crystals in the pellet. And thymine, that's a nucleobasis you have normally in your DNA. And typically, when you make the Fourier transform of these guys, I mean, these terahertz fields, you can see that you get a rather flat spectrum for the reference field. But I mean, for the thymine transmitted field, when you make the Fourier transform, then the spectrum exhibits several holes here, located at specific frequencies, and this signals that a fraction of the terahertz energy has been absorbed by the molecule to excite some rotational or translational motions inside the molecule. Why? Because the terahertz waves you see are electromagnetic entity whose beating or the characteristic period is about 1 picosecond, and 1 picosecond, that's a typical time scale of rotations and low translations of molecules. So you can use that objects, these terahertz waves, to get some information about the internal motions of complex molecules and macromolecules. And when you revert, for instance, this absorption, this transmitted spectrum with respect to the reference spectrum, I mean, you get what spectroscopists call the absorption spectrum. That means that the holes here are transformed into peaks, typically. And these are the absorption peaks at which you can excite some rotations or some translation. And to understand them, what is common to do is to compare these experimental spectra to ab initio simulations, like using the DFT method, for instance, that will compute for a given molecule, a molecule of thymine here, that will compute the elementary phonon modes and their frequency and their amplitude. So the energy, typically. And you can see that the location in the frequency range and the height of these peaks are in reasonable agreement. And once you have that, you can image the movements of your molecules. In the typical case, when you look at what happens at 17 terahertz, you can see that you excite dipole in the vicinity of these functional chemical groups. So this is what we have done by using moderate intensity, moderate laser intensity, so 10 to the 13, 10 to the 14 watt per square centimeter. Now I would like to end this first part of my lecture on the terahertz waves by telling you that you can produce much more energetic terahertz pulses. The process that relied on the photoionization of gases I have just described allow you to produce some terahertz waves delivering a few microjoule in energy, which is not so bad. That corresponds usually to 10 to the minus 3, 10 to the minus 4 in terms of laser to terahertz conversion efficiencies. But you can get much higher energy when you use relativistic plasmas to enter into a relativistic regime. When you make laser plasma interaction, you need to increase the laser intensity typically. And once you exceed the threshold of, let's say, 10 to the 18 watt per square centimeter, you can make it possible to accelerate your particles, electrons or ions, to speeds that are close to the velocity of light in vacuum. And typically, once Kim, which is now well known in this domain, is to build up some laser wake field acceleration setup. Typically, you have a laser pulse, which is here, that interact in a Gauss cell with a gas of a noble gas, let's say helium, and it will start to ionize it. And above all, when it operates at an intensity which is much above the threshold of ionization. But at this intensity level, the laser has a very pregnant and important ponderative force. This is the mechanical force of the laser exerted on the electrons, first, on the charged particles. And at this intensity level, what the laser do is to expel the electrons in such a way that they are completely extracted from the atom. And the electrons are going to oscillate around the ion background, around the ion site, and develop what we call an electron plasma waves. And this electron plasma wave has a good idea first to have its typical frequencies belonging in the terahertz domain when we ionize a gas, typically reaching some electron density of 10 to the 17, 10 to the 18 cubic centimeter. And they can be arranged under some resonant condition in such a way that the plasma wave, which is emerging here, remains connected or follows the light pulse by remaining in its wake. And when you operate at very high laser intensity, what you see here is some accumulation of electrons, periodic accumulation of electrons in a nonlinear relativistic regime, which is so intense that the electrons having the highest energy, some of them can be trapped in the cavity, in the plasma cavity here, and be further accelerated through the ramp of the electrostatic field, which is attached to this electron plasma wave. And this is the principle of the laser wave field acceleration, through which, I mean, you can accelerate some electrons over a few centimeters to very, very important energy above the giga electron volt level. If you use these schemes, this principle, for making some terahertz waves, then you can exploit another mechanism which is what we call the coherent transition radiation. This is a mechanism that was discovered after World War II by Ginzburg and Frank. And the principle is that when you take a bunch of charged particles passing from one medium, the plasma, to another completely different medium, vacuum, then to assure the continuity of the electric field, the transverse component of this electric field at the interface between the two materials, then you need to add a linear solution to the Maxwell equations that represent a spherical wave, which is of electromagnetic nature, and which is able, to propagate at the velocity of c in vacuum. And its spectrum is very broad, depending on the Lorentz factor of the bunch of electrons, and that can extend to a relatively broadband value in the terahertz range. So you can reach typically 90 terahertz. And here you have a snapshot of an image computed from a particle in cell code. This is a kind of ab initio code we use for describing the dynamics of plasmas. Where you have here, you have the laser pulse that went out from the plasma anteriorly created by laser matter interaction. And you see here, you have a lobe that corresponds to the photoionized process I first described. And as I told you, well, it can only generate a few microjoule in terms of energy. Typically, we simulated here laser Gaussian pulses operating at a high densities, 10 to the 19 watt per square centimeter, and containing also two harmonics. So having 10% of second harmonic, just to creating the same process as I've just described before. The main difference is that since you can accelerate electrons in such a relativistic plasma, some of them are so accelerated that they exit from the plasma. You see, you have a fraction of them. They have about 10 mega electron volt in energy. They can go out of the plasma, and when they go out of the plasma, they create coherent transition radiation at the interface between the plasma and vacuum. And as they propagate, they emit a radial lobe of a terahertz pulse. And it happens that the energy corresponding to this process, it is about 100 times more than the one I've described at the beginning of my talk. And it corresponds to terahertz fields that can be of several tenths of gigavolt per meter. So this is a way for producing very intense terahertz fields. And well, the question now is to know what to do with that. And for instance, do they field ionize? Okay, this is what I wanted to tell about my current research in physics. And of course, I didn't do that myself alone, but with several collaborators in Denmark, in Germany, in France. And I wanted to take the present opportunity to thank them very much. So this was the first part.